Good afternoon, ladies and gentlemen. So we are Team 5, and my name is Da Gang. And in our group, we also have Guan Shen, and also Yun Zhen and Ian in our group. So the company we're cooperating with is called InterAgent, and our project title is about predicting the PCB factory cycle time in order to increase the customer satisfaction. So before moving on to our project, we want to have a brief introduction about the company that we are working with. So InterAgent is established in 2018 and is spin-off from the NTHU AI Intelligent Center. And the company they have been providing is concentrating at providing the APS, which is Advanced Planning and Scheduling System. And since they are a service-based company, so their main SaaS product is called Sarah. The full name of Sarah is Scheduler Agent and Resource Agent. And so for their customers have from various industry, which includes also PCB, which is printed circuit board industry, and also auto parts and also IC design companies. So why does company need the Sarah system? It's because that these kind of industry are some industry that includes some complex manufacturing. So by using the Sarah system, there are some advantages, which they can give you the forecast for their delivery, which they can predict the cycle time for their product. And they will also show the load analysis, which will tell you like what's the load right now in the factory. Do we need to increase the orders or decrease the orders? And they can also come up with the automatic report for the company. So they will also have a more efficient production for their company. So for the Sarah system, they can reduce 90% of their scheduling time and also increase the productivity by 20%. Okay, so the business problem for our group is that we want to increase the customer satisfaction by predicting the cycle time, which we want to have a good accuracy of the prediction. And the previous accuracy for factories without using the Sarah system is only 30 to 50%. So the action for our group is to create a high accuracy model. And the stakeholder for our project is InterAgent and also with its customers. So as I mentioned, the clients are from PCB, IC design, and auto parts company. And one of the challenges for our industry is that if we come up with a low quality forecast result, the customers will be disappointed at us and it will cause a poor customer satisfaction. And there are also some humanity considerations, which is there are some privacy for the clients, which if we didn't secure the business data for the clients, it may cause some problems to the companies. So moving on to the machine learning goal, we are focusing on the cycle time for the PCB, which is from fab in to fab out. And as you can see on the photo, this is a photo for the PCB, which it will have different kinds of shape, different kind of size, different kind of thickness. So the production method is different for each PCB. And for the types of our machine learning goal is a supervised learning goal, and it is also predictive, and which is also a forward-looking, which the analysis is ongoing forever. And the outcomes for our prediction is the seconds, which is the time for our prediction. So next, we're going to hand it to Leo, and he'll talk about the our project.
So my part is going to talk about data and how we do the model. So initially, we have two kinds of data. One is raw data, and one data is raw data with a sub-process loading in the PCB manufacturing process. And we found out that when we use the raw data sub-process loading data, we can have higher accuracy. And so we choose this data, and there is around 35,000 columns, rows in the data, and 74 columns. And each row means a PCB work order. And for data preprocess, we derive the variable, which is called aspect ratio. So the aspect ratio is a numerical input. So the range is from 0 to 15. And when the aspect ratio exceeds a number, the order will be considered as difficult to produce. However, we found out that it's not easy to define the threshold of aspect ratio, and we cannot find it's correlated to other predictors. However, we use a different way to set the aspect ratio at 7, the threshold at 7, and we will explain later. And we also replace the mixing value with the average of other inputs. And data partitioning, we have 80% of training data, 10% of validation data, and 10% of testing data. So on the right side, we could see that in the input variables, initially we have 74 columns, and we reduce it into 58 columns. And the output variable is seconds, what we just have mentioned. And it's quite interesting that on the right side, we remove the predictor called ounce, which is the thickness of the PCB. And it may be highly correlated to the seconds of the production time, but we remove it. We also remove a predictor called MO number step, and which is also related to highly correlated to the seconds of output. However, due to some reasons, we remove it. We will explain later. So the method we choose is decision tree, generalized linear regression model, deep learning, which is neural network, and what's a tree? So we're going to predict the output, which is seconds. And first of all, we look at the relative error of the output, and we found that decision tree have a lowest relative error compared to neural network. And it's kind of funny because a neural network takes about more than 30 minutes to run on my MacBook Pro M1 because I only have 8 GB of RAM. I don't have that much money. But however, decision tree only takes me about 30 seconds to finish all the process. So after we choose the decision tree as our model, we need to calculate the absolute error in order to calculate the accuracy. So absolute error is the prediction minus the true value and take the absolute value of it. And after that, we could see we use absolute error lower than 1 base, which is 96,400 seconds, and divided by the number of data rows. And what I mentioned in the previous slide is that we need to define the threshold of the aspect ratio. And we could see that when we set the aspect ratio of threshold at 7, we have the highest accuracy, which is at 85.1% of accuracy. Okay. So I just mentioned about that we use the data with sub-process loading. In this part, we could see these inputs are the sub-process loading data. So it takes most of the weights of the input and output compared to the normal like attributes. So this is evaluation, and we can see on the left side is the prediction and the true value of the scatter plot, and it's really highly correlated. And we also calculate the absolute error that lower than 2 base, and which we can increase the accuracy to 95.3%. And it's really fun that we found in RapidMiner, the auto model, there's a feature called extract data information, and we didn't select it because if we select this feature, the model will be overfit, which the absolute error is 0.1% with overfitting. So we didn't choose that as a function. So we're going to give you some conclusion and recommendations. So in this case, just like I mentioned, the sub-process increased the accuracy because of lower relative error. So raw data have 24.6% of relative error. However, the raw data with sub-process is lower than that. And we can also see on the right side, we just mentioned that neural network take much more time than the decision tree. Then when I run the neural network, it also burns my computer. So the one attribute that I have mentioned is ounce, because in ounce that the data is kind of complicated. It's combined with Chinese numbers, English numbers. So we find it's really difficult to clean the data. So we suggest that when the factory enter the data, they could enter the data in a more formal way to calculate the ounce in the prediction. So the second one is define the aspiration to 7. So the threshold of 7, when the number is bigger than 7, is hard to produce, and lower 7 is easy to produce. And the variable M1 number set is the meaning of is it hard or easy to produce. So in our decision tree, we find out it does not influence the outcome. So we think that maybe the factory need to change it to another type of attribute to in the future in order to have a higher accuracy in our model.
Okay, and then so as Leo mentioned, the methods we choose as decision tree is because that the efficiency of the computation. So this chart is basically the runtime for this is for the deep learning, and this is for the decision tree. So as you can see, there is a large gap between the computation. And for the models we choose, this is for the accuracy, relative error for decision tree, which is only 8%. And the model we choose for the deep learning is 10%. So based on our model, we think that the decision tree we use has a higher accuracy and also has a higher efficiency. And the other suggestions we have is that based on the model, we could predict dynamically, which is every week. And we can also predict before each analysis, which is a one-time analysis. And by doing so, if we found that the accuracy is getting lower, we could come up with a new model, and eventually we could have a higher accuracy for every analysis. Yeah, and so this is basically the conclusions and our findings for this project. Thank you.
Thank you. Okay, wonderful. So first of all, let's allow the people from the company who have been touching this data for a while. Do you have any questions or comments that you'd like to give the team?
Actually, we're using the deep learning model.
Yes.
And they have our GPU, so we can different model. So, I think the model you're choosing is very important for our business decision because you save lots of time to training the model. So, when we try to say predict dynamically every week, it will help us to reduce our resource to our computer resource to training the model and increase our business value.
Okay.
Thank you.
Thank you. Anybody else want to ask any questions or comments? Yes, Patrick, please go ahead.
Yes, so I'm not surprised that that the deep learning model didn't do too well with this data set. I think there's another very important advantage to what we do is that decision trees also gradient boosting approaches they just always work. Whereas the deep learning, they can spin out of control and produce nonsense. It's just way more stable.
Yes.
So that's another very important advantage of your work. But the one thing that I was a bit perplexed by is that your training set was like 60,000 samples or something like that.
35,000.
35,000. Okay. Yeah. I was a bit surprised that the gradient boosting approach didn't do better. That's like that's my major question. Did it do a lot? Was it like maybe an overfitting problem? Did it do very well in sample, but then not do too well out of sample? Or like, do you have an idea why that is?
The gradient boosted tree's accuracy is relatively lower than the decision tree, but so that's why we choose the decision tree as our methods. But like we were trying to find out like if there's any possibilities causing this, but we did not find like the relations between it. Okay.
Okay. You maybe do like an analysis of like you showed me like importance factors, but I think this was right from the linear model, was it?
Yes.
Yes. You also like the importance factors in your tree or like the gradient boosting?
Yes, but we didn't put it on the.
Okay,
yeah, sorry.
Is it maybe that there's just one or two or three variables that are like super important, the other ones didn't matter? Or is it more like variable?
So we mentioned about the process loading is more important than other variables, which is the working order of each station. The station means there are many stations in the factory, right? And in each station is being a different process of making the PCB. And the order loading in that station means how the working load of the whole procedure.
But again, this is using a linear model, right? This is produced using a linear model, not your decision tree. So how did you get this?
We got from the decision tree and by the linear model and the refinement of the model.
This is the boosting, this is probably the random forest results.
This is the decision tree result, but yeah, we didn't put the linear result on it yet.
Oh, okay, because you don't wait, so I thought it's the weighting linear again.
No,
Okay,
no, no.
so that answers my question.
Okay.
Thank you.
Thank you. Yes, go ahead, please. Missing values.
Yeah, we're taking the average of other values at the same attribute.
Okay, that makes sense, yeah. Thank you. Thank you. Any other last questions?
So we talked a lot about the prediction performance. So what can the company do with these predictions from the decision tree?
Like our
Actions can
like because InterAgent use the neural network as their model, so like what based on our findings, they maybe can choose like decision tree in the future. Maybe they can try like using the decision tree as a model. It may come up with a higher accuracy. Like maybe that's our like
And also
findings,
with
yes.
higher efficiency.
Okay, thank you very much. Okay, our next team. Our next team is, where is our team? Okay. And this team was also tackling a similar problem, but you can see that they're actually looking at it from slightly different point of view. Let's send this one forward. If you need to go back. Okay.
Good afternoon, everyone. Today, we are cooperating with InterAgent, and this is our project predicting a factory delivery time or cycle time to reduce operational costs and increase production efficiency. So first, introduction of InterAgent. So InterAgent is a provider of an artificial intelligence dynamic scheduling and planning system using AI, and their system is called Sarah. So it gives us benefits to factories such as reduce scheduling job time, schedule dispatch feasibility, capacity efficiency optimization, and increase productivity and reduce invalid wait times. So the business problem, here's the problem. First, poor estimation of delivery time will result in production inefficiency and increase in operational costs. So there are a lot of wait times. Basically, we don't know if the product's going to be 3 days, so we cannot schedule ahead for the delivery, and it creates a lot of wait times in between of production process. So the action is create a predictive model that can predict delivery time. So the stakeholder is InterAgent and the clients for InterAgent. So as for today, it's PCB, IC design, and also parts. So the opportunity here is it can significantly improve customer and client satisfaction. So I want to put it here because I think this is not the most important point, but it is like collateral benefits to it. And this is, I think, pretty important to discuss because machine learning model can be misused by the clients. So what is the actions from the clients? It's gonna affect the labor welfare. This is just one example. For example, okay, the model is gonna predict in 3 days, but actually it's gonna produce in 5 days. But you force the labor to work it in only 3 days. So the problem here, the machine learning model is used as a decision tool, not a prediction tool. Okay, that's only one ethical considerations among many. So here are the data mining goal. So the goal is to predict the delivery time of PCB production, supervised, forward-looking, and for predictive purposes. So in our team, what is a success? It's to predict delivery time with minimal cost and high accuracy. So cost is pretty important, but we're gonna discuss it later. And to create, this is only the cycle, is to create a simpler model. To yeah, and the outcome variables is time in seconds. So this is a lot, but so data source we use raw stock process loadings. So it shows its particular PCB order from the customer. So this is the input variables, process and loading. So it maybe some order need a certain process and what is the loadings on it, item status, quantity, the sizes of the PCB, and here are the output variables is predicted seconds. So our partition, training 70%, validation 20%, and testing is 10%. And here are the methods. We are following the methods of the InterAgent. So we're cutting into 28 days to cut some outliers. Then we encode some categorical variables. So for variable selection, we decided to use two, lasso and decision tree, to make sure that they agree with each other. Therefore, we know that that variable is maybe redundant. And for modeling, we use linear regression as a benchmark. We also use decision tree, random forest, and neural nets. So the performance metric we use is also mimicking what InterAgent does. So this is again, this is the benchmark. If you use linear regression, the MAPE, mean absolute percentage error, is 13 on trading and also 13 at holdout. This is the APE. And one cell in here, so 77, is basically if you take the data from 1 day to 10 days, how many of that data of absolute error is less than equal to 1 day. So this is the one cell here. And this is training and the validation. So I think the runtime of the model is also a great performance metric because it tells us, okay, how many long that it took to run. And the hardware used, we also note that for comparison purposes. And here, so let's talk about the complexity of the model. So here are the biggest weaknesses. I think they're really noticeable. Number of parameters. It's really hard to optimize neural nets because there's a lot of parameters and it's unstable. Sometimes we get runtime of days, sometimes in minutes. This is in 1 minute, so I think it's impossible. Sometimes it takes like seconds. So we're not sure why, but honestly, because we haven't learned a lot about neural nets, that's why we cannot optimize it. So here the MAPE, it's not bad, it's realistic, but it beats benchmark. So here are the hidden layer 2, rectifier, number not 64. Epoch is I think the cycle is 3000 with learning rate. We're following the InterAgent learning rate, and the momentum is 0.99. And here, noticeable is we only have 2 parameters to optimize. After a lot of researching from online communities in data science, we found out that just set the tree depth to maximum and just tune the number of trees. So technically, we are only tuning the parameter of 1, only the number of trees. And we found out that it's kind of not overfitting. So you can see that validation and holdup is not that different. And also the runtime is significantly faster than the deep learning. And so the next question is, how good is the model? We apply it. We obviously we see a lot of 90s and 80s. So the managers are saying, okay, let's use it, right? But we haven't talked about money because money speaks more, right? So here, so Okay, so we have created some cost analysis. Here are our assumptions, and basically our assumptions also have some research on it. Basically, our assumption is if it's early, then we're gonna store it, and then when it's due, and then we're gonna deliver it. And this is the right cost, so we have 0.5% penalty fee. And obviously, we can use any assumptions later, but in here, it gives us a lot of insights. If you decide to use our model, here are the costs. Actually, the early cost is higher than the late cost, but it gives us also what will be the customer satisfaction. If you are early a lot, it doesn't affect any customer satisfaction, but it's gonna cost a lot. But if it's late, then maybe your customer will be irritated, but it's gonna cost a bit less. So it's good to find a balance between the two and communicate it properly with the managers and clients. So here are our recommendations. So the advantages of our model is you can predict delivery time with high accuracy and cheaper models to run. And the cost analysis provides much higher level of insights to clients and managers. So some limitations, we do not take into factors we don't do other factor of productions. So maybe some other factor of production that are important, such as number of workers. How good is the machine? What number of machines do you have? So we don't have that. So our operational recommendations is to retrain the model annually or after significant changes. So it's also provides real-time solution. It can also potentially detect some problems or anomaly in production process or order. Maybe order is abnormally high, or maybe some workers, maybe it has an abnormally large errors inside. Maybe the workers have something or machine have something we don't know, but it can potentially detect some problems. And it can also create automatic security system. That's a bit obvious. So that's for our presentation. Thank you very much.
Okay, thank you very much. Does anybody want to, do you guys have any comments about this approach or?
I think we need to think about the cost analysis.
The cost analysis. Okay. Yes.
Maybe it was on the slides with the numbers. I don't know, but where do your residuals lie? Because you talked about the cost analysis.
Yeah, this is
And there was a bunch of, so is this where the actual predicted residuals are?
yes, this is the residuals, yeah.
Okay.
So this is the error in
Okay.
terms of days.
Perfect. Okay, thank you.
Any other questions or comments? Okay, go ahead, Patrick.
So both of these groups that were working in the company were very concerned about like training time. I wonder why. I mean, if it's trained like once a year, or if it's trained like, you know, maybe when something significant is changed, but shouldn't happen too often. Like, why do we care about 1 extra minute of training time?
Do you mean why do you train the model?
No, why do we care so much about training time? Because both of the first group, you as well, you were very, very concerned about training time. But training time.
The
The time.
Oh, training time.
Yeah.
Yes, training time, yes. The time of training it takes to train the models. Why do you care so much if it's only once a year?
Maybe it's more interpretable, or maybe we can run it locally without having an advanced machine, because as you can see, neural nets or deep learning requires a heavy machine. So we can run it locally. Of course, there's some advantage to it. So we don't need any cloud computing. So we can run it offline, maybe. Yeah. So runtime is like a measure of complexity for simple model. Yeah.
Understood.
Mhm.
Great, thank you very much.